class here. So we did some work around clustering, and we basically looked at k-means. So how to use a k-means for clustering. That's how to use to separate data points or data to their different cluster, to the different group they belong to. Okay, so I'm still gonna go through this stage 4 in the module. And in the stage 4, we'll be looking at these learning objectives. How we can use scikit-learn k-means class. Then understanding the important parameters. There are some parameters that are very important in k-means. Then there is the concept to call k-means initialization. That's k-means plus initialization. Thereafter, we do some rework on real looking data. I'm not going to take time on it because it's been part of our last classes. So the first thing is we need to have idea of how to use scikit-learn and call for k-means. Now, scikit-learn is no more new to us, and there are reasons why we use scikit-learn. You can optimize your work with scikit-learn. With scikit-learn, you don't need to start writing code all over from the scratch. You just import what is already existing, and that makes your work very fast. Then it's able to handle some cases, we call it edge cases. Another thing is that the k-means algorithm in scikit-learn has a smart way of initialization. That means how to initialize your procedure in a smart way. So then you use k-means plus plus. Okay, so we went through some code which helped us do some clustering. Then here in this second code, we basically imported k-means and we make some prediction with the import. From scikit-learn, here we're using .cluster. Sorry, I need to run this previous one. So from scikit-learn.cluster, we import k-means. So this is the class that handles the k-means algorithm for clustering. So we define an object km, initializing it on k-means. And these are the parameters we use here. So for this case, we just use number of clusters to be 3 and random state to be 0. Thereafter, we use predict function and feeding function on the x that has been designed and that has been defined up here. So x and y true are defined through make blobs function. So the make blobs function helps us to create some data points. So here we're taking 150 samples followed by centers 3. Then the standard deviation of the cluster, we use 0.5, the random state of 0. So that is what we defined x. So what we're doing here is to fit and predict on the x that you have created. Okay. And at the end of the day, we have these results printed out. We have 3 clusters, 0 to 2. So each cluster is divided into 50 points. So that's what k-means library, so k-means class does for us here. Instead of starting all over from the beginning, writing code from the scratch. So by using k-means, we just have few lines of code and we're able to get the number of cluster or the number of points in this make blob case. Okay, so if we want to check the results, we want to visualize the results. So there's a visualization. The centroid for each of the class is the star. So for cluster 1 in pink, we have the centroid here. For cluster 2, we have the centroid here. Then for cluster 3, we have the centroid here. The next stage is to look at the parameters that are used for k-means. So we use some parameters and they are outlined here. N underscore cluster, that's number of clusters. In this situation, just put 8. So that's number of clusters. That's number of k. The init function, that's how do we initialize? That means how do we start? How do we start the process? We use the k-means plus plus. It's used as initialization method. Then the number of iteration, that means how many times do we go from beginning to end, from beginning to end, from beginning to end. So we go 10 times. So that's also a parameter. That's number of times to run with different seeds. Then we have the maximum iteration. So that means for the first run, I go 300 times. Second run, I go 300 times. That means for 10 times epochs or n initialization. So I'm going to go 300 times 10, which is 3,000. Then the tolerance is used for convergence. Convergence is at what stage is it that I don't have any need to adjust the centroid again. So there's stability now. That's the last point. So what happens? Sometimes you might not get perfect 0. But when you have a value of 0.0001, that's fine. That's convergence. So tolerance for convergence is taken as 10 raised to the power minus 4. That is 0.0001. The random state, so you could set it to null, you could set a value. So this is used for reproducibility. So these are the main parameters. So can you read it after me?
The main parameters, okay. N cluster equal 8.
Don't worry about the values, just go with the
N clusters.
Okay.
Init.
Okay.
N underscore init.
Okay.
Max underscore inter.
That's iteration, okay.
Toll equal LE.
That's the toll is tolerance. This one is 1 raised to, this means 10 raised to power minus 4. When you see 1e, then a value. So this means exponential to -4.
Okay.
What do you say?
Okay.
Yeah, so it means exponential to -4. And that means you have us 10 raised to power minus 4, which is 0.0001. So close to 0, because in real life, we might not have 0 convergence. That means we don't have them. The value is coming to 0. So 10 raised to power minus 4 is fine. Okay, so let's take these parameters one after the other. So the first parameter here is n clusters, which is number of clusters. So that means how many number of k are we using? How many groups are we creating? Okay, so that's the first thing. N clusters, that's the most important parameter in k-means algorithm. That's the most important parameter. So here, it means number of clusters to find. So you specify it before your experimentation. Okay, then we'll learn more about this in stage 5. We're still in stage 4. How do we choose the number of clusters? So we're going to talk more about it at the next stage 5. So that's the first thing, the clusters, n underscore clusters. The second one is the init. So how to pick the initial centroids. How do you initialize your centroids? Because for k-means algorithm, you need to beforehand set your centroid. So how do we first of all set a centroid? So we use the k-means plus plus method to do that. So what does it do for us? It's an initialization method. It is randomly picked. And when you pick something randomly, it might be bad, it might be good. So it's try and error. Then another better way of doing the initialization is k-means plus plus. So instead of just randomly picking, so there is a smarter way of selection. And this is a default value actually, and it's a recommended method that you should use k-means. So instead of using random for the init, that's initialization time, you use k-means plus plus as a recommended smart selection method. Okay, so here is just to show how we compare the results we get when we use random init with k-means plus plus. So the difference might not be that obvious, but when we do reproduction or when we go deeper, there is actually a great advantage of k-means plus plus over random. So k-means plus plus is a better way. And this code, I'm not going to take time to explain this, to talk about these lines of code. So this is just a subplot, 14 by 5. So here we're using loops methods loop function to do a plotting, focusing on random and k-means plus plus. So the zip here is used because we are combining two variables. Okay. And this is just a setup for training, for using k-means function. And this is just to predict what you have treated at the other side. Then this is just an iterative way of running in a range of 3 using randomization and using k-means plus plus. Okay, then the other ones are just a normal setting for plots. Here we arrive at this. So when we use random and when we use inertia, so random versus k-means initialization. So here we obtain these results for each cases. For init of random, this is the init with k-means. So here, when you have init with random, see the centroid where it is occupying, and see the centroid where it is occupying here. You will notice something, that the clustering points for the blue color here is different. Here, you see at this side, that's for the k-means initialization. The blue point comes into the midpoint. So approaching higher value of y and the mid value of x, but in this place, lower value of y, then lower value of x, or mid value of x and mid value of y and lower value of x. So this gives us the results when we choose to use randomization to initialize and when we use k-means plus plus, recommended and default way of doing randomization. Okay, let's run this part. So the third thing is the number of initialization. You remember we're talking about the parameters. So the first one is the n clusters init, and for init, that's initialization. You can use k-means. You can use what? Apart from k-means, you can use what again?
Clustering.
From here, apart from k-means,
can also use init random.
Random. So you could use init k-means. You could also use init random. Which one is preferred?
K-means.
K-means plus plus is preferred. Okay. So that's the second parameters. So the first parameter is the number of clusters. Okay. The second parameter is the k-means plus plus. Now the third parameter is the number of inits. That's the number of times to run with different seeds. So that's how often do I run? Okay. So let's explore that here. For this third one, which is the number of running, the multiple times of running. Okay. Is the number of times to run k-means. That's the first thing we need to know. Then it runs with different random centroids. So for each time you run, different centroids are used. Then at the end of the day, it returns the best results. The best result is the lowest inertia. We're going to talk about inertia again. Then default is 10, and it's usually enough. So that means for k-means algorithm, the default value for running our iterations is 10. So when we run 10 times, we good to have a very appreciable and satisfactory result. Okay. So you could see here, when we run our k-means here, again, it's the same code for running. We initialize, instantiate an object km with k-means class, setting number of clusters to 3. That's a parameter. Init to random, the number of inits to 1, the random states to seed. So the seed value has been set as for seed in range of 20. That means the number will be checked from this random state. You'll be using different value from this seed number in the range of 20. And it keeps picking different numbers for the number of iteration to be determined. So initially, we set our inertias to 0. So we are gathering results here. So it is set to 0. That's empty list. And we use a loop statement for seed in range of 20. Remember, number of iteration tells us the number of times to run the k-means. And because it's not one time, so in this situation, we need to use for loop. But you will notice here that the value is set to 1 here, okay, just for teaching purpose. But we usually use 10, okay. So we do the fitting, then after fitting, we append the results. So the result is appended. And the result that is appended is a km.inertia. So inertia will be got, and this inertia value will be appended to the inertias that we've instantiated. So dot append had this value. There's a value we'll get with k-means.inertia. We'll append it to inertia. So this is the inertias we set out as empty lists. So as we run the experiment and iterate through the values we've set, different values of inertia will be generated. And as they are being generated, we are appending them, we are adding them into this empty list. And at the end of the day, we make a plot. So what's our plot? Our plot is taking this state, we're taking the range as the x-axis, we're taking the inertia as the y-axis, and we're setting the color. So this one, just the color settings. Then for the horizontal line, so the horizontal line, this dashed line, the horizontal line. So this set for the horizontal line, and also we set for the, that's the AH. So we plot a AH line, then we'll plot a H line for when Y max is, for the Y max of inertias, the other horizontal line for the Y minimum. So you see the red line here, the red is when we have the maximum inertias. Then the green, you could see it's not showing, the green is not showing. That means our inertias do not fall below 0. So that's why we know, so there's no value that is low below, that is between 0 and 70 at the minimum level. So you even see that this line is consistent. It's showing that all our inertias are actually max, their maximum value. So the horizontal line, so this is set, and it takes the minimum inertias. This one takes the maximum inertias, which is the worst, then the best would be the minimum inertias. Okay, now we plot the X label as a raw number. That's the label for X, then the label for Y. Inertia, so we set this. So these are just setup. These are just setup. Okay, the main thing I need you to take note of is this part. This is a part of the code that actually determines what. So inertia is instantiated on 0. Then we run a seed of range of 20 rather. Afterward, we train the model with k-means, or we run the model on k-means class, setting these parameters, number of clusters, init random, number of init, one random state, we use a seed. So the seed value is changed all the time. So that means the number of time to run each seed is 1. We don't want to go more than 1. But the seed will be changing, the value will be changing. Okay. And at the end of the day, we have this 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So those each of these bar represent the seed value that is used at every point in time. So that's why we have 20, and at every run, we don't run it more than one time. That's the number of inits is set to 1, but the random state is changed using a range of 20. Okay. So what else do we talk about here? Now, the title is why init matters. Different runs give different results. So that's just what we want to see here. Then why init, with init is 10, scikit-learn runs 10 times and keeps the burst. This prevents us from getting stuck with a bad result. So this is just to show how to explain the number of inits as a parameter. Then we have the max iteration. That's a fourth parameter, max iteration. So max iteration simply means maximum iterations. By maximum iterations, we usually set the value to 300. So iteration means that if I run once, if I want to go 10 times, so each time I run, how should I run it? How long should I run it? So that's a max iteration. So we usually set it to 300, meaning that for every time you run, don't go beyond 300. That's your maximum iteration. Sorry, let me respond to that. Is it making sense to you?
Yes.
Do you have a question here?
So far, no.
Okay. Okay. So let me continue then. So here, the fourth parameter is max iterations. And for this max iterations is the number of maximum iterations allowed. So the default again is 300. And for this, it's been observed that the convergence, when I say convergence again, it is a time where the value drops to 0 or close to 0, and there is nothing to update again, nothing to update. So we say, okay, it has converged, and it has come together. Okay, so that is, but we usually use 300, but we don't normally get there because convergence usually happen much, much faster than that value. Okay, so we want to check how many iterations we actually need. Most times, the number of clusters defined here. So this is a parameter. Again, you see k-means, we're calling it as a class, passing on to it number of clusters, a random state to 0, the max iteration, we're taking max iteration to 300. So this is what we want to check. So we want to check which is more. Is it going to be the number of iteration or the, so how soon or how fast do we achieve convergence? Okay, so that's what this part, what you want to see from here. And here we shows that maximum iterations allowed is 300 is the default, converges faster. Then the actual iteration used is usually 3. Let me just run this code, see. So it means this code has run, the training has happened, and it was discovered in the course of the training because we ask it to find for us the km dot number of iter. So this is an internal attribute in the k-means class, is an internal attribute. So after the code was run, number of iteration, you could see when you see this underscore out at the right hand side, it's telling you it's an internal parameter inside the class. So it's been evaluated and the value was found to be 3. Meanwhile, our maximum iteration was set to 300. So meaning, are you talking, sir?
No.
Okay. Meaning that our number of iteration is actually lesser than the maximum iteration. Okay. So that's what this part is explaining. Actual iterations use 3. How do we know it's 3? We got it by this formatting. We did a placeholder here and said return for us whatever the value of number of iteration is using the dots operator of with the km. And km is the k-means that we have, the object of k-means that we have instantiated with these parameters. So these parameters have been executed on the k-means class, and the result has been obtained. So this is a value that is obtained. Okay. So random state is seed for random number generator. So when you say a generator in randomization in mathematics, so you need a seed to generate, like you need a number, just like something that we start, that we use to start the generator. So every time you want to run your generator, you need, okay, let me give you an example. You know, sometimes when you go to some malls, you have some toys there, but those toys are locked. So they will tell you that for you to run those toys or those, you need to drop some coins. So those coins you are dropping are the seed to generate or to run that machine. So when you want to run number generator, there is a seed you need to drop. So here we drop a number, and that number will be the seed for running the generator. So the random state is just the seed for random number generator. So you set it to a number for reproducible result, because we need to run the experiment again. Somebody might want to try what you have done before. So when you set a value, it will ensure that when another person is running the same code, it's going to have the results you have had. We've talked about this extensively before now, okay? And it's also good for debugging when there is error and you want to check what is going on. It's good for that. So that's another parameter random state. So far, so good. We've covered these parameters. Let's go through them. Can you read them for me now again and see if you understood them? Okay, the first one.
So n cluster is for the number of clusters.
Okay, which is a k. Okay.
What?
I said, which is k?
Yeah.
Okay.
Init is
so,
the what?
Which one of them is the most important one? Most important parameters?
The most important is definitely the k.
Okay.
Cluster.
Yeah, which is n clusters. Cool. Yeah. So that's the most important. Okay, continue.
The init is the initialization method, which is k. K means plus. Then init is the number of times it can run with different seeds, and that's 10 times. The max iter. What was iter again?
Iteration. That means
is
how
the maximum iterations per run.
Yeah.
The toll is convergence tolerance, and the random state is for reproducibility.
Okay, so those are 6 parameters are very, very important, and we seen how we can use them. Okay, so with scikit-learn, we are good to go. We don't really have much problem using k-means. Now, let me talk about this part 3 here. And for part 3, we want to call check two attributes. We call them attribute after feeding. So the dot feed and the dot fit predict. Okay, let's run this code and I'm going to explain this. Now, I was talking about the internal attribute the other time. Here, when we talk about the number of iteration. So anytime you run your k-means, there are some values as the algorithm is run. There are some values that have been generated. You don't see them until you call for them, you ask for them. So one of them is the number of iteration, then underscore after it. Now here, km is an object. You can call it anything. You can call this anything as anything like, but k-means is a standard class. Now you can see that here, out of the 6 parameters we just talked about, we're just using 2 here. And you could see why this is the most important. Even though we dropped others, we didn't drop it because it's the most important, okay? So number of clusters, we've taken 3 and we fit it. So we're fitting it on X that had been created before, which are those blobs that we created, okay? So say the first thing here. So the first thing is we want to find out the cluster centers. So you can see again, see this cluster underscore centers, then underscore. It means it's a variable inside. Sorry, it's an attribute, sorry. It's an attribute inside of this k-means. Okay, let me quickly search something. What are the attributes in k-means? Okay, these are some of the attributes. Output attributes. Is this guy giving me what I want to show? Okay. This attribute must be specified by the user. No, these are the parameters. Let me see the internal. Yeah, this is what I was looking for. Okay, you can see it says in the context of the k-means algorithm, internal attributes, often called model attributes or properties, especially in implementations like scikit-learn, are the characteristics of the fitted model. This is important, the fitted model, the trained model that describe the resulting clusters and the algorithm's performance. So they will not be there, they will not be shown until you call for those attributes. So these are determined after the algorithm has run to completion. That means after this, after you've run km is defined as k-means, taking this parameter, and you have fitted it. So that's when you can call for those attributes, okay? And the key internal attributes of the k-means model include the following: the cluster centers. So you can see it's internal because how do we know it's internal? You see this this underscore at the right hand side without anything following shows us that, oh guy, this is the internal, this is an internal attribute of this particular class we're considering. So cluster centers, which also stand for the centroids, of course, centers. So this is the coordinate of the k centroids representing whatever. The other one is the labels. So another one is a label, labels underscore. So this is cluster labels. So the label is usually from 0 to k minus 1. So it's assigned to each individual input data point. Don't worry about those things. Just focus on this. Inertia underscore is another attribute. Then another one is number of iteration underscore. It's another attribute. The number of features in is another attribute. Then, okay. So that's just what I want to show. You could read it further if you want to know more. But the point here is explaining this. The dot fit and dot predict, dot fit underscore predict functions. So after we have filtered our model or we have trained our model, we want to do certain things. Number one, we want to find the cluster centers, which is the final centroid positions. How do we go about that? We call on it, use dot product with cluster centers, just like we saw here, cluster centers. So this one will tell us the number of centroids, okay? Then the second one is the labels, So what does that do for us? The labels, you see, it shows us how each label is assigned to each individual input data point. So this will indicate which cluster a data point belongs to. So that's about this one, the labels. The next one in this class is the inertia attribute, internal attribute. And what does that do? You know, inertia?
Yes.
It measures how internally coherent the clusters are. I mean, it measures how close to one another those data points are, how close they are to one another, and how far they are from other cluster. So how close are we as a group, and how far are we from other groups? Okay, so it's a measure of how internally coherent the clusters are. So this has a formula. It has a mathematical formula where you take the difference of, don't worry, you take the difference of the data point and the centroid, you square it and you sum them together. Don't worry. So we always want to have a lower inertia. A lower inertia shows that we are united. So let me use that term. You know, in families or in organizations, they say, let's be united. Let's come close together. So that means let our inertia be so low. So we're together. And inertia in K-means measures that, it shows how tighter the data points are in the particular cluster. Okay, that's about that. Then the next one here is the number of iterations. So this is another attribute. And for this number of is the number of iterations the algorithm took to converge. I mean, how many times does it run before it attains a convergence point, before it sees that there's nothing to change again. Then there's another feature which is not included in that my preparation. It's called the number of features in underscore. That is the number of features or the dimensions that is used to train the model. Okay, let's see what we have here. Now you see, we have the following. After we run this, we have the following. For the first one, the cluster centers, which is the final centroid positions. So we have this vector. Then for the labels, that means the cluster label for each point. So the first 10 labels use one. So these are the labels that are used for them. So it's telling us the internal workings. What are the things that really happened inside of the model? The inertia. So this is within cluster sum of square. That means how far apart, or how close are we as a member of the family? Cluster is a family. So how close are we? How united are we? So the last value, the best result was 72.48. And this means it shows that the mean points are close to their centroids. Then the next one is the number of iterations. So for this particular case, the number of iterations was 3. Now we may also want to see this one, the features in. So all we just need to do is to pass in this into this place. So let's create another print statement here. Let me do something here. So let's just do So I want to put number of features in. Okay. And I want to include this. I change this to 5. Change this to number of features. In. So that's the number features used for training. And that is the dimension. Okay, so let's run this again and see what we have. Okay, you see the number of features in the k dot number of features in return for us value of 2. And that is cool because we use, let me show you something. Where's the initial place where we started? Oh, made a blob. Yeah. Okay. There's something I'm looking for. Okay. So yeah. Okay. So it returns this value of 2, showing us the number of features, the dimension. And of course, you can see just have 2 dimensions in this situation, the X, the Y dimensions, the features used for this training. Okay, this next one will be a practice exercise. You might try to look at it and see how you can try out your end on those stuff. So the key summary point here is this. K means it takes number of clusters, which is equated to K, and very simple to use. Then we have the K means plus plus. So this is used for smart initialization. And there's a default. Another one is the random in it. So that one usually can give bad results. So we prefer by default K means plus plus. Then the number of iteration shows us the number of times to run for the best result to be achieved. Then how do we access our results? The internal values. So you could access by your cluster, status underscore, labels underscore, inertia underscore. These dots, it will be your object dot whatever you call your object. For instance, if you call your object Tochi, is if for instance you say Tochi is K means, so you cannot change this, of course, K means, but you can change this. K, you can change this one. Let's say I make it Tochi and I want to know the attributes internally. So I'll just say Tochi dot cluster underscore centers underscore dot Tochi dot labels underscore Tochi dot inertia underscore then Tochi dot feature in underscore Tochi dot number of I3 underscores. Okay, so the next stage for us will be to find out how to get optimal number of clusters. How do we get optimal values? So how do I know that the clusters I have obtained are enough? I don't need to get any one again. So what do we do? That will be the stuff we're going to address at the next phase. But let's go through the objectives again and see if we have been able to achieve these learning objectives. So the first objective is said, we want to use scikit-learn's k-means class. And we've been able to use that. Did we?
Yeah.
Okay. Then understand all the important parameters. How many parameters did we cover?
We covered 2.
How many?
Actually,
how many parameters did we cover?
5.
Oh, okay. Yeah, we covered 6 actually.
Oh,
So
okay.
can you list 2 out of them?
The names there was one that used K and the iterations.
Oh, cool. So we have the number of clusters.
Yeah.
Then we have n iter. Okay. Okay. Then the initialization also, where we use k-means or we use random. Cool. Then practice on real looking data. We did a practice by checking those parameters out. So we're going to move to stage 5. And at stage 5, we'll be looking at something called elbow method. So these points, let's set the stage by considering the objectives we're going to use here. So the learning objectives, number 1, we want to understand why choosing K. Why is it a challenging endeavor? Why do we find it difficult to choose K? So that's one learning objectives. The second one is to learn the elbow method. So I want to learn what the elbow method is. The next one will be that we'll practice finding the elbow in a plot. So when you see that, you understand. Then the last thing here is to apply the method to real data. So let's set it out now. The problem is, how many clusters are good enough? So that's a problem. That's a big challenge. How do we know the number of clusters? Because in k-means algorithm, you need to specify beforehand your number of clusters. Your k must be specified beforehand. So we call it a priori, beforehand. Priori, A-P-R-I-O-R-I, a priori, beforehand. But if you don't know how many natural groups exist, how do we choose? So if I don't even know if there are 20 groups or 30 groups or 3 groups. So this supposes this idea of choosing k-means beforehand presuppose that I should have some idea of how my groups are, but that's not true in life cases. I might not know it beforehand. So that's a challenge. Now, if I choose a k value that is too small, what will happen is that groups will get merged together. If I choose a value that is too large, what will happen is that natural groups will split apart. They will get split apart. Choose small value, groups get merged together. If I use too large value, then there will be separation. So those that should stay together will be splitted. That's not good. So we need an optimal value of k to ensure that all the data points fall into the correct group. Does that make sense?
Yes.
Cool. Now the next thing is we do a kind of demonstration. For this demonstration, I imported make blobs. So make blobs is a function in data sets, which is a submodule in scikit-learn library. Then we use k-means, which is imported from scikit-learn.cluster. Then our usual matplotlib and numpy. So we want to do a creation. We want to make blobs. And we call this blob with creating, we pass it into X and Y throw. So those are the two stuff we're using, the two dimensions we're using, X and the Y throw. Now, we set the number of samples to 300, the centers to 3, cluster to the standard deviation to be 0.6, and random state to be 42. So the next thing is we want to try different values of k and plot it out. So by doing that, we have an axis or figure. Then we set the axis, we flatten it, k values. So because we want to try different values of k, So you have 2, 3, 4, 5, 6, 8. The next thing, let's just check the plots we generated and try to associate it with the code. Now look at this. When k is 2, when k is 3, when k is 4, when k is 5, when k is 6, and when k is 8. So let me try to show. I want you to make some comparison yourself and see what you can make out of this. Okay, can you look at this plots? What can you say about each of the subplots?
Well, some x's are not generating. Some are too close together. More x's that needed are generating. The colors are joining. That's what I can observe.
Okay, now let's pick it one after the other. Look at when k is equal to 2. K is equal to 2. Then take note of this red cross. And when k is equal to 3, take note of the red cross in relation to the purple blobs. These are the purple blobs. So let's focus on the purple blobs. Now, when k is 2 and when k is 3, what do you say about the blobs?
The purple blocks, when k is 2, are separated.
Okay, so that's splitting, right?
Yeah.
So then when is 3, what about that?
They all are matching their red X.
Okay, so you will notice that when k was 2, the red cross stayed in between these two groups. They are splitted. When it's 3, it stays the cluster. When k is 4, again, the red blob, the red cross is in, but look at the green and the yellow. As they're actually supposed to be together, but now they're splitted. They're splitted because of the value of k. Now, look at when k is 6. These guys that should be together, they are splitted. These guys are splitted. They are supposed to be together. So what you can see is that when the value of k is growing up, there seems to be an increment in kind of internal, I call it internal agitations. So they are breaking apart and breaking apart. So there's division coming in as the value of k goes up. So what we notice here is that when k was 2, two groups merged. When k is 3, this looks good, as you can see yourself. When k is 3, you see how they stand on their own. These guys stay together, these guys stay together, these guys stay together. See, when it was 2, these guys that should have been together splitted, and they now have this in between them. So we have it very good when k is 3. Okay.
Yes.
I was explaining, yeah. So when k becomes 4 plus, so we'll just have unnecessary splitting. You could see here, just here alone, we have 3 splitting. Here we have 3 splitting. Here we have 3 splitting, just to make sure that that 8 is accounted for. Because the number of splitting is going to be the number of cluster of, you know that. So count the number of red crosses, 3, 6, 8. So to fulfill that 8, just scattering, just splitting what is not supposed to be splitted. So we have it good only optimally when k is 3. Even here, when k is 4, you could see these guys should be together. They are splitted. Now, that means it's very important we choose our k properly. So the question now will be, how can we choose k automatically? Since we know that the beauty of our algorithm is dependent on the value of k. So what do we do then to ensure that any k value we choose is the optimal value of k? And that leads us to the second part, the inertia. So in inertia, we call it within cluster sum of squares. So what does this do for us is, in inertia, look at your family, for instance, in relation to another family. I want to see how cohesive you are. So there's going to be, it's going to be a thing of concern if you are closer to someone from another family than you are to your family. I'm sure you know that.
Yeah.
For instance, if a child is closer to another person's father than his father, then there's a problem, isn't it?
Yeah, that's it.
So they want to, so let's assume we can measure the closeness. And when we measure the distance between this man and his son, is, let's say, feature space. Now, you remember when we talk about feature space measurement, let's say is 5 units. This son and his father, 5 units. But when you measure the feature space of this son and another person's father, is 2 units. Is that a problem or not a problem?
That's a problem.
There's a problem because the child is closer to another person's father than his own dad. So there's a problem. So we want to see that. So inertia is what helps us to achieve that. We want to note, want to see, or want to set up the fact that anytime we are measuring within the cluster, there is going to be a kind of cohesion between the data points. And the way we achieve that is the inertia. This was the formula I was trying to explain the other time, that you take the distance between the data point X and the centroid of that data point, then you square it and you add them up based on the number of samples you have. But don't worry about this mathematical expression. That's just the idea of inertia. Inertia is the sum of squared distances from each point to its centroid. Okay? Now, the key thing you need to know here is this. When points are closer to their centroids, that is better clustering. When daddy, mommy, children are closer than they are to another group or family, then that is low inertia. Now, when you add more clusters, your inertia will be reduced. That means you are creating more separation and splitting. So there are some extreme cases where the K, which is your number of clusters, will be equal to N. And at this point, it means your inertia is 0. So that's an extreme case. Okay, that's the idea of inertia. So inertia is just to see the internal cohesion, internal agreement within, internal closeness within clusters in relation to the external cluster. Okay, does that make sense?
Yes.
So we just simulate something with this code, and in this code, we just want to see the different values of K and the corresponding inertia value. So we want to calculate some range of values for K and see what we get as the inertia for that. Okay, so here we have, we're just taking a range. For our K range, you just take a range of 1 to 10. That means 1 to 11, that is 10 data points. Then inertias, since we don't know what inertia is yet, so we're going to instantiate it on 0 list. So it's empty list here. And that means we're going to append our value of inertia to this result. So we have instantiated our inertias on 0. Now, it's important we use loop function here. And we say for K in K range, that means each value of K, meaning 1, 2, 3, 4, up till 10. Those are our K, each value of K. So for each value of K in this K range is a container. So it's like you have a basket of apple containing maybe 10 apples, and you go there, you pick one out. That is a K in the range of K range, in the range of basket of apple. You hit that, you go back again, you pick another one, that's another K. So this function is doing that. It will pick a value in this box of potato or box of whatever, picks it up, eat it, go back there to this range. So this is a container. Now, because we're picking this range, we now need to set up a function that uses what we're picking. So the function that uses that is we are instantiating an object km, and we're calling the function kmis that we already imported from scikit-learn. And of course, we've talked about some parameters that are very important, but in this situation, we're just using 3. And of course, number of clusters is important. And for a number of clusters, we are making it to be the value of each of the k we are picking. K1, K2, K3. Each of the k we are picking is the number of clusters. The random state is set to be 42. Then the number of initialization, 10. You remember that's the default value. Okay. But there's something we didn't put here. We didn't put maximum iteration here. We know that most times the convergence is obtained before the maximum iteration. So we don't really need it. Now, the next thing is after we have created or we have instantiated our object km, we feed it, that is, we train it. And it's taking this argument of x. You remember in those times, in those periods when we were dealing with what's it called now? Supervised machine learning. You remember we usually fit our model with X train and Y train. But because this is unsupervised, we don't need Y train here. So we only fit it on X. So we fit it on X. Then after fitting it on X, as we train it, because we are using different value of K, so the first training, an inertia value will be generated. So you will take that inertia value, you go and drop it inside this basket of inertia. So that's what we are doing here. We are dropping inside the basket by using append. So after training, let's say I pick K is 1, I put 1 here. So 1 will be here. I train this model, I feed it. Then there is an internal inertia that will be generated when 1 is used. So I'll pick that value, I'll go and drop it inside this inertia. That's what this code does. Inertia.append. What am I appending? You are saying append for me the inertia underscore. Inertia underscore, you remember, is the internal attributes in kmis. So kmis has an internal attribute, inertia underscore. So it will pick it, it go and drop it inside this inertia and store it there. Then it goes again, that's a loop. The system goes again and pick a value of k is equal to 2. Again, it will train the model with that value. As it trains it, it also generates some values, some attributes. But what I need here now, I just need the inertia. I could also create another thing here. For instance, I could create n iter here and also do a kind of empty and again append it to this. But I don't need that. But I'm just showing you that inertia is what we are focusing on now. So I could also do some other attributes and store them. So after we've done that, then we create a dictionary. We print out a statement. This statement will contain the value of k and the corresponding value of inertia. Okay, let's see what we have. I hope that explanation is well understood.
Yeah.
Okay, so let's see. Remember, we're taking a range of 1 to 11. That means 1, 2, 3, 4 to 10. So when k was 1, inertia was 19,884. That means when k was 1, the distances between the data points, the mean value was 19,884. When k was 2, inertia was 335. When k was 3, inertia. Now, what do you see? As k goes up from 1 to 10, what happens to inertia?
It also goes up.
Are you sure?
No,
K,
it actually reduced.
Yeah, it's reducing. So it's the opposite. Yeah. It's inverse proportion. As k was 1 here, inertia was 19,000. K grew to 2, inertia dropped to 5,000, drastic change. K grew to 3, inertia dropped again drastically to 204. K grew to 4, inertia dropped to 179. So you can see that as k goes up, inertia comes down. So that's it. Inertia always decreases as k increases. It makes sense.
Yeah.
How does it make sense? The more cluster means less distance to the nearest centroid. Now, so you have seen how this happen now. So the next thing is we are going to the stuff where we call able. Able. So what happens? What does able address? So we're going to do a plotting and you see something. So the idea behind able is this, that I will get to a point where even if I create, okay, let's see something here. Let's assume, okay, let me even practice it here. Let me change this to 20, or maybe I change to 15. Let me change my range to 15. And I want to show you something. Okay, see, even dropping further here. Let's see what happens at 20. Okay. Let me save 35. Okay. Okay. Now you will see that as it increases, the value is still also dropping. But the point is that I need to come to a spot where I say, I'm fine. This dropping is enough. It's optimal for me. Okay. We must come to that point. So it is the able that helps us achieve that. You see, can you form your able? If you make your able, that's the idea of, can you make an able symbol? Able. So if you see your elbow, you will notice that your fingers point upward, right?
Yeah.
And it goes down. As you trace, if you trace down your hand, you use your finger to trace your hand. So it will be coming down. Then it will get to a point where your elbow will be straight with your shoulder. Do you understand that?
Yeah.
So that means at that elbow point, okay, this is what I'm showing. Can you see this? This looks like your elbow, isn't it?
Yeah.
Yeah. So this is your hand, the tip of your finger, and down towards your hand, and let's get to this point. So this is your elbow. This is the elbow. At this elbow point, nothing is really changing again. Nothing is changing. So that's the idea behind elbow. Now let me explain again with this. When you plot inertia versus k and you look for the elbow, so the elbow will be the point where when you had more clusters, it doesn't help much anymore. Now take note of that. It doesn't help much. It doesn't help much. It did not state that there's not going to be changes. For instance, when I put it to 20, you will notice that at 15, I had 52, 49, 45, even though there is still dropping. But I might decide that I think it doesn't help more anymore. It doesn't help anymore at 13. So let me just drop it at, let me make K is 13 as my elbow. Because it's not that you'll not be getting results. You'll still be getting value that will be dropping, but you need to know when it doesn't help much anymore. It doesn't help much anymore. So it is able principle that helps us know when it doesn't help much anymore. Does that make sense?
Yeah.
Okay. Now, the curve bends at able, the curve bends and start to flatten out. Okay. Now, think about it. You have one room and you have 100 people in that one room. So what you're going to experience is what we call super crowded room. One room. Now I mean the same number of, the same dimension. I mean, normal average dimension, because one room might be as large as a stadium. So I mean in normal rooms size. So it will be super crowded. So when you have two rooms for 100 people, it will be much better. When you have three rooms for 100 people, it will be improving, right?
Yes.
So when you have 10 rooms for 100 people. That means each person, that means 10 people can share one room. So there's barely any improvement over 9 rooms. So when you have 9 rooms, it will be some people, some room will have 9, some will have 10. So even though with 10 rooms, you will still have people, you share them equally 10 across. But you can still achieve the same value, the same result in a way with 9 rooms. So if I can achieve the same, if I can achieve almost, please mark my word, almost the same thing with 9 rooms as with 10 rooms, why do I need to waste more money getting the 10th room when there's barely any improvement over 9 rooms? Now imagine I say, oh, I want my people to be very convenient, then I get 100 rooms so that each one person can be in the room. What will happen is that it becomes wasteful. So the idea behind EBO is where adding more rooms stops being worth it. Where adding more rooms stops being worth it. And that's what we have shown here. So with this plot, we have shown that at point 3, it's wasteful if you make your K 10. Okay. If K is 10, it doesn't make sense because you will see that there is virtually no difference from point 3 to point 10. Do you understand?
Yes.
Okay. So you see now, let's read this plot from K to 1 to K to 3. Inertia drops rapidly. That means from here, from K to K is 1 to K is 3, there's drastic drop. Here it was 20,000. At here is 5,000. There are 3, just drops straight to almost 0. But actually, it's not perfectly 0, but it converges very drastically. So this shows that 3 gives us the optimum value. Any other thing we had there does not really worth it. So after K is 3, inertia drops slowly, diminishing returns. Like when you are very hungry, maybe you've been fasting for days or you've gone out and you're very hungry. And once I get my food, I'm going to devour it. But after you've taken some spoons, you just notice that you are saturated. Has that happened to you before?
Yeah.
Yeah. So that's the diminishing return. So that point where you're saturated is the EBO point. Okay. And that is the explanation here. So here it is just showing the same thing. And this is practice for you. You're going to do some practice on your own from part 4 in the code, part 5. Okay, let me talk about this. So when the EBO is unclear, there are times when EBO is unclear. So what do we do? Look at this. If you look at this plot, you will notice that the EBO point here seems unclear because there still seems to be a kind of dropping as we move towards each point. Can you see?
Yeah.
So here now we say this point, we say the EBO point is unclear because we can't just say here that it's flattened out. So what do we do when the EBO is unclear? So there are certain things we can actually do, and I'm going to talk about them. Number 1, we can use domain knowledge. That means based on your understanding, your experience. Okay, you can just, how many groups really make sense? Okay, let me just go for instance, I may just, I think 5 seems okay for me here. Somebody might say, okay, I think 4 seems okay. But for me, if I were to choose, I'll just choose 5 because after that 5, there's still for me a little kind of obvious drop or obvious change between 4 and 5. So I'll just say, okay, I think 5 is fine for me. So you might choose another value, maybe 4, another person might choose 6. Okay, but of course, I will not want to choose 10. That would be wasteful. Okay. So that's the first thing. That means you use domain knowledge. How many groups make sense? Then there's something we're going to look at is stage 6 of this class. And that's the next consideration, which is called, it's called silhouette method. So you try this method. And what this method helps us to do is, so you can try that method, then you look for the range of reasonable K values. Then you consider the practical use case. So these tips are very important. You use domain knowledge, you try the silhouette method, and you look for the range of reasonable K values, or you consider the practice use case. Okay, does that make sense?
Yeah.
Okay, let me
Do you
run
have an
this.
example of the silhouette method?
What do you say?
Is there an example of the silhouette method?
Yes, that's the next class. That's the next class.
Okay.
Yeah. So that's the next class. But you can read about it before the class. Okay. So the summary for this is we have been able to calculate initial for K from 1 to K max. We have plotted an initial inertia versus K. Then we found what elbow is as the place where curve bends. And we talked about knowing your optimal K. So the key point here is we know inertia always decreases as K increases. Then the elbow is where improvement slows down. Then we also learned that sometimes the elbow is unclear. So when elbow is unclear, what do? We use domain knowledge, we use silhouette method, we use a range of K that makes sense, then we consider the practical use cases. Does that make sense?
Yes.
Okay, thank you then. So I'm going to send you the scripts. Please do well to read a silhouette method before the next class, and any concern, reach out to me. And on that note, we're going to call it a day here today. Thank you so much. God bless you.
Thank you, sir.
Okay, thank you, sir.